Hello and welcome everyone to this new video in our series about OpenGl ES using Java for Android system. This video will be the last video in our series. I think we already now made a good progress, so we already have a scene with multiple objects and we can rotate and translate these objects. We also have lighting and a skybox. In this last video, I will try to do some cleaning, and while doing this cleaning, I will be adding a feature which is removing objects from the scene, and I will also enable adding new objects to the scene, and we will test this feature. In the deleting, we will be focusing on deleting the OpenGL resources such as textures, programs, and buffers. Then I will introduce the combining of motions. For that, I will be adding the moon. For the moon, I will be adding a rotation around itself. Then I will be adding a rotation around the Earth. And then the moon and the Earth together should be rotating around the sun. I will show how you can do this by combining rotation and translation matrices. One important thing about rotation and translation, when combining them, you should be careful about the order. So here in the upper part of this figure, I will show a case where we have a square. Here I marked one corner of this square, and we have the origin here, this red point. So now if we first rotated this square with 45 degrees, you can see that this point will become here on the bottom. So after that, if we made a translation by a amount which is larger than the size of this square, then you can see now this point is translated here. Now, if we reverse the order of translation and rotation, you can see that again here, in this case, we marked this corner of the square. Now, if we translate it by the same amount, now the point is here. Then if we followed up by a rotation with 45 degrees, so remember this point was somewhere here, and now it's rotated by 45 degrees, so it's up there. And you can notice the difference here. So now here, this is the origin. You can see that this point is clearly above, on this axis here is above the origin, while here it's using the same axis here, it's below the origin. So it would have a minus coordinate in this axis, while here it will have a positive. Let me explain this using a simple Python program. If you don't know Python, don't worry too much about this. I will be going quickly through this also in Java. So basically what I'm doing here in this Python program is that I'm constructing two matrices, one rotation matrix and one translation matrix. And I'm doing this using homogeneous coordinates for a 2D space. So since we have a 2D space, we only have X and Y coordinates, and then I will add another coordinate to combine the translation with the rotation in a one matrix, as we shown in the beginning of this tutorial series. If we're now in a 2D space, X and Y coordinates, then this matrix here will be rotating around the Z axis with an angle A. And this A, as you can see here, we are taking it to be 45 degrees. And for the rotation matrix, we will add a column which is 0, 0, 1 here, as you can see. Let me show this rotation matrix. So you can see that this is a 3 by 3 matrix. This part here will be doing the rotation, and this column here is added together with this row here to incorporate the translation to this matrix. And then we have this translation matrix. So in the translation matrix, we change only here this last column. So as you can see here, we are translating with a 3 on the x-axis while it's 0 on the y-axis. And then I'm constructing 4 points. These are the 4 points. You can see here the xy coordinates, and I'm adding here a third coordinate because of this homogeneous coordinates here, where we want to do the translation and rotation using one matrix. Then here I'm first multiplying the translation with the rotation matrix and then multiplying the result with P1. So now each point, like P1, would be first multiplied by the translation, will be translated, then rotated. And let's see the result. This looks the same as our second row here. And let's now go to this case here. And now if we reverse the order, so let me comment this line and have this line here activated. Now you can see that P1 will be multiplied by the rotation matrix. So we are doing first rotation, then translation. Let's run this code. And now this would be the result here, which corresponds to our first column in the slide here, this case. So now in our Java code, we will be doing a matrix multiplication. So we'll add a matrix multiplication function for this, and then we will be doing a rotation for the moon around itself, then making the translation with this distance from the Earth. Don't worry, I will be going through it again when I'm writing the Java code. So now let's go to our Java code. So in the Java code, let me first go through the cleaning stuff that I did. So let me open the changes using Git. And let me start by the objects which are a part of our core package. There we have the vertex buffer, and as you can see in the vertex buffer, so this is just changes in the import. Then here I added this destroy function, and in this destroy I am deleting the vertex array and the buffer. If you remember here in the constructor, we are creating a vertex array and a buffer. So in the destroy, we need to delete these two. And that's it. Similarly in the texture, so when we load the texture here, we generate a texture. So we need to delete this in the destroy function. For the program, I did a little bit more cleaning. So I removed all these four variables and changed the load function a little bit because I discovered that we don't need them. So basically the IDs of the shaders can be kept as local variable, and the code I was keeping it anyway for just debug purposes. So now here, after creating a program and attaching it to the shader, I can safely delete the vertex and fragment shader, as you can see here. So what's left to delete is only the program which we create here. And you can see now in the destroy function, I only call the function delete shader on the program ID. And that's all the changes here in the program. Now in the base object, I added a new property called isInitialized. This property will be used to initialize objects which we will add after initializing the scene, as you will see later. I also removed the ascene reference here from this destroy function. This will affect all the classes derived from a object. Let's go through these classes now. We have many of them. For example, here, the sphere object. So another thing which is common in these classes which are derived from a object, that all of them require a program and sometimes a texture. The program and texture deleting will be handled in the scene, since the scene is also responsible for loading those. That's why in the destroy function of these objects, we don't need to take care of these. The only thing which actually we need to take care of is destroying this vertex buffer. You can see that here on the function on destroy, we're only destroying this buffer. And that's it. The same for the skybox and for the B object and for the BCTN object, as you can see here. For the BCTN object, I did another two changes. So one of them, I added this function set uniform color. So if you remember in our last tutorial, we added this uniform color to our object. However, we did not have any function to set it. And that's the purpose of this function. And then I also found a bug, which is in this line here. When setting the uniform of our shader, we were setting the has uniform color to 1 if the uniform color is null, and 0 otherwise. Actually, it should be other way around, as you can see here. So that's it for this class. And also for the wire object, the same here. You can see we only have the destroy function where we destroy the buffer. So now we went through all these classes here. Now let's go through the camera. So in the camera, nothing has been changed. So in the camera, destroy function does not do anything since we only here defining these float variables. Let's go now to the scene. So in the scene, I added an update call. So for this update call, I defined this class scene update call interface. It's a simple interface. It has only one function called update. I will be using this update call later to add or remove objects from the scene, as you will see in a minute. I also added now a remove object. So the remove object is straightforward. You just remove the object from the objects list and then destroy this object. Now in the init function, after initting the object, we set the initialized property to true for this object. And now when we are updating or drawing the objects, we first check if it's not initialized, then we initialize it, then we call update. Similarly here for the draw, we first check the initialized, then draw. Now the destroy function of the object is more involved since we have objects. So we have to iterate through the objects and destroy all of them. Then we have to iterate through the programs and destroy all of them. Again, through the textures and also destroy all of them. Then we need to destroy the camera. And here in the draw function, as you can see, after updating the objects, I am checking if we have this update call is not null, then we call the function update. Here we will be adding and removing objects from the scene. And other functionality could be also added here if you want. And now let's move to the input and scene class. So the input class has this list of receivers. These are objects which implement the iReceiver input. One kind of this object, for example, is the camera. So now we are checking if there is no receiver. Actually, we don't need to handle this touch event anymore. And then in the destroy, I only clear all the receivers and put the gesture detector to null and remove all the click listeners. Now in the scene destroy, first we destroy the input and then we call super.destroy, and that will allow the A scene to destroy all objects, textures, and programs in the scene. So one problem I had when I was implementing this destroy is that this scene class set itself as a renderer for the surface, and it also sets the on-touch listener for the surface. When I tried to set the renderer to null, this gave some exceptions, so that's why I was not able to do this. So I decided instead of that just to put the surface to null as we saw earlier, and then in any of these three callbacks from the surface class, I first check if the surface is null and then I will return. And these three callbacks were the surface created, surface changed, and draw frame. One small also thing which I added here is in the update FPS, the number of objects in the scene. So as you can see here, I just added objects, colon, then the size of the object. And that's actually all the changes in the classes. What's left is the shader and the main activity. So in the shaders, I only did small cleanings. So I discovered that this out has color is not needed since I will initialize the color here anyway, either to ones or to the color from a uniform or from a color attribute. Then also in a fragment shader, I had to remove this out has color, and I just set the fragment color to the output color which we will get from the vertex shader, and that's it. Now in the main activity, I added a new button. I called it close button, and this close button will just call activity.finish. So let's see that in the main activity. So this is the callback for this button, which only call finish. And when the activity is finished, then this function onDestroy will be called. And in this onDestroy function, if the scene is not null, then I will call destroy scene. Then I will call super.onDestroy. And as you can see, I also removed these variables here. I also added some code here for testing, adding and removing objects. I will go through it later. And that's basically all the changes. And as you can see, our program still runs as before. Of course, now we have this close button here and the number of objects as you can see in the top. Now let me show you how I implemented the adding and removing of objects from the scene. So for that, I will be using the function setUpdate call from the scene, and I will be setting this callback to the function sceneUpdate. This is a nice feature from Java. So previously I was using the lambda expression, and the lambda, if you remember, would be something like long timestamp and a scene, and then I call sceneUpdate ts and obj. Then actually Android Studio has suggested for me, as you can see here, to replace the lambda expression with a method reference. And if you did that, you will get this nice syntax here, which is shorter. Now let's go through this scene updated function. So for this function, I will be using these two variables here. One of them is a random variable to generate uniform random numbers over all the possible integer values. And I will be using a list of bctn objects called the cubes. This list will be used for adding the new created objects. So in this function, I will be basically creating objects and adding them to this list and to the scene. And then later, I will be also removing objects from the scene. And for that, I will be removing objects which are added into this cubes array. So let's go through the function. So as you can see here, I'm repeating this loop here 10 times, where each time I will be creating an object and then adding this object to the scene and then to this cube list. So let's go now through creating the object. I will be using this function from KubeVert, which we did in a previous tutorial, called create with one file texture. Then I will create a bctn object based on the vertices from this KubeVert. And as you can see here, I will not be adding an attribute color. I will be adding a texture, and there will be no lighting, so no normals here. And we'll be using this 8 colors texture which we used also in a previous tutorial. For a uniform color, I will be generating a random color. That's why you see here red, green, and blue. So the generation is very simple. So this rand.next integer will give us a random integer. I will take an absolute value because this integer could be negative, and then I taken it with the mode 256 and dividing it by 255 to get a floating number which is between 0 and 1. The same repeated here. Now we have our color. We use this function set uniform color to give each cube an extra color component. Then for the position, I'm again using this next random number and I'm taking it mode 40. So this x would be now between minus 40 and 40, and then here it will be divided by 10. So the x coordinate will be between minus 4 and 4. For the y coordinates, as you can see here, we are taking the next integer with the absolute value and then mod 100. So it would be a positive number between 0 and 99. And then here we will divide it by 10. So it would be something between 0 and 1. And then shifting it by 8. So it would be between minus 8 and 2. For the z, I will be only putting it to 1 always. I made these choices for the x, y, and z values just to make the cubes appear in front of the camera without needing to navigate through the scene. Finally, here, as you can see at the end of this function, I have a loop which will make sure that we don't increase the 200 cubes. So if the number of cubes is more than 200, then we will take a random index and then we will remove it from the scene and also from the list itself. And that's it. Let's run. Now you can see that the objects appears in a random position, and also notice that each cube has different color. That's because we made the position and the uniform color component random. Notice that also here we have the number of objects always 205 because the scene have originally 5 objects and we are not allowing more than 200. Of course, at the beginning we'll start by 5, then we'll increasing 10 by 10 till it reach 205, and then it will not increase anymore. Notice also that the frame per seconds is dropped to 8.5. That's because we are having many objects, namely 205 objects. Each one of these objects having its own buffer and its own draw call. That's very slow. This can be made faster by having all the drawing of these 200 rectangles done using one buffer and one draw call. However, I will not go through this in this series. And that's all what I wanted to say about this first part of this tutorial. So in the second part, we will go through motion combination. And for that, let me first here deactivate this call. Then let us add the moon below the earth. So for the moon, we'll be using vertices from the sphere vert2 class. And I will put the moon here as a member variable because I want to handle the rotation of the moon from inside the rotation of the earth, since both they will be rotating around the sun. And in that, I will be avoiding doing some computation twice. And let me also scale the scene a little bit down. So for the earth, I will be using 0.4. For the moon, we are using 0.3. And for the sun, let me use 0.5. So as I said before, the sizes does not reflect the real size of these objects. I just want them to show on the screen and not be very small. Now we also need to add this texture for the moon. So we should put it inside the images. And that's it. Actually, now we have the moon. So if we run, we will not see the moon because it's inside the sun. Now we need to handle the movement of the moon so that it appears rotating around the earth and then together with the earth around the sun. Let's do that. As I said, for that I will be using the same function for the earth rotation. So this function called move earth, and in this function we were using this variable theta to track the angle of the earth around the sun. I will add two angles here also to track the moon, so the moon around itself and the moon around the earth. So now if you remember here, we were decreasing this theta angle around the sun. Then we are computing the position of the earth. For making the earth motion, we were resetting the translation to 0 because we want first to rotate the earth around itself, which is done here in this line. We were rotating the earth with 5 degrees around itself. And then we set the translation. And now the rotation of the moon will do it in a different way. Namely, I will be using matrix multiplication as I showed in the slide at the beginning. And for that, I will first set the moon model matrix to identity. So we need to add this function as you see here. And then I will increase the rotation of the moon around itself and around the earth. I'm using the same step. That's not good because the moon will be facing the same side of the earth always, but I will keep it like this for now. And let me now add this set model to identity. So we will do that by simply calling matrix.setIdentity for the model matrix of the A object. Then I will now define some temporary variable which I will use for the different matrices. So I will use A, B, C, and D, and I will set them all to identity at the beginning. Now the matrix A, I will use it as a rotation matrix for the moon around itself. So as you can see here, call the function rotate M for the matrix A with the angle moon around itself, and the axis will be the y-axis. Then matrix B, I will use it to translate the moon to take its position with respect to the Earth. So imagine now that the coordinate system is centered at the center of the Earth, how much we need to translate the moon so that it gets in its actual distance from the Earth. So now I put it as 0.9 because we are using very small distances. So I think for the Earth, we used 0.4 and the moon was 0.3 size. So using this 0.9 will already take the moon a little bit away from the Earth, but we also don't want to make it too much so that it will not hit the sun when it's rotating around the Earth. You can play with these numbers later if you want. Now we need to rotate the moon with respect to the center of the Earth, and for that I will use the matrix C. As you can see here, now I'm rotating with the angle around the Earth, and I will use the matrix D to move the moon with the Earth around the sun. So that's using this current position which we computed here and which we are translating the Earth with it. And now let me go to this mat util and add the function to multiply two matrices. Let's put it somewhere here after matrix vector multiplication. So as you can see, this function takes two variables, and I'm already assuming that those are both four matrices, and this function is simply create a 4 by 4 matrix represented by this red variable, and then for each entry of this matrix, we will compute it using matrix multiplication, so be the corresponding column of B multiplied by the corresponding row of A. And now using this function, we can combine all these matrices as following. So we have combined transformation, I called it ctran, and this will be simply multiplying these matrices starting from A. So this would be A multiplied by B, then multiplied by C, then multiplied by D. And now we simply need to set the model matrix of the moon to this ctran. And for that, I need to go to the model matrix and make it public. And that's it. Let's now restart. You can see now we have the moon rotating in a funny way around the Earth. We need to play with these parameters here, how they are increased to make this motion a little bit better. So let me maybe try to make the Earth slower. And notice now that the moon is rotating around the Earth with the same speed that the Earth is rotating around itself. So basically, some places of the Earth will never see the moon. Can make it different by making the moon maybe slower around the Earth, maybe 2.5. Let me also enable this update here. So now you can see all the things which you implemented in this video, and that would be it for this video. Thank you for watching, and as I said, this is the last video in this series. I hope that next year, so in 2025, that I will be able to start a new OpenGL series where we can do more advanced stuff. So if you have a topic in mind, please write it in the comment, and don't forget to like and subscribe to the channel. Thank you all, and I hope to see you in the next series. Bye.